All right, today we're going to finish up chapter 13 and start on chapter 14. All right, so here we have a reaction mechanism. All right, so we have two steps in our reaction mechanism. So you have step one, the first one, step two, the second one. And you see that this is a rate constant K. It is K sub 1 because it's for step 1. And you see rate constant K2. That just means it's the rate constant for step 2. This was done in the lab. This is an experimental data to find that the first step is very slow. And then the second step is very fast. Anytime you have the slow step, it has to be listed for you in these problems that ask for the rate law. The slow step is called the rate determining step. So the easiest question on the test is which one of these steps is the rate determining step. The one that's labeled slow determines the rate. All right, so if it takes 8 hours to drive to the store and 2 minutes to pick out the item, the rate determining step is the drive to the store. If the drive to the store is 2 minutes, but you're going to spend an hour in the store, then your rate determining step is the time that you were in the store. So the slow step, the step that takes the longest, that is what is determining the rate of the reaction. So anytime you're given a reaction mechanism, it will always tell you to give the overall reaction. So just like in Hess's law, anything on the right that's exactly the same as something on the left will cancel out. In this case, it was the F. All right, and so then you have your final answer for the overall reaction. 2NO2 plus F2 goes to 2NO2F. All right, so the F does not show up in the overall reaction. So the questions will always include label the reaction in intermediates and catalyst. And catalyst. All right. So the difference between the reaction intermediate and the catalyst, the similarities are they don't show up in the overall reaction. The difference is the catalyst is something that you put into the reaction, just like we did on Thursday. We added the copper solution to, we added the catalyst to make it go much faster. And the thing that took 12 minutes only took 1 minute. So it made it very fast. All right. So a catalyst is something you add. A reaction intermediate is something that is formed in the reaction. See, in step 1, you form the F, and then it's used up in the next or any other reaction so that the overall reaction, it cancels out, doesn't show up. You do not add a reaction intermediate. It is formed and used up. You must add a catalyst. So when the question is determine the rate law for this mechanism, you get the rate from the rate determining step. Again, the rate determining step is the one that's labeled slow. These are elementary reactions, which means we use the coefficients to write the rate law. And so rate is equal to K, concentration of NO2, concentration of F2. And since NO2 is a reactant and F2 is a reactant, that is your final answer. All right, when the first step is a slow step, this is a very, very easy question. When the slow step is not the first step, then it gets much more complicated. All right, so the rule for a rate law is it cannot, so rate law cannot contain a reaction intermediate. All right, and so the problem with the second step, if I just reverse this and the second step was a slow step, then you would have rate is equal to K, concentration of F, concentration of NO2. All right, that cannot be your overall rate law for this mechanism because F is a reaction intermediate. The rate law cannot contain a reaction intermediate. So then you would have to do more algebra in order to cancel out that F. which makes the problem much more difficult. All right, so again, here is another easy mechanism question. I say that because the first step is labeled slow. When the first step is labeled slow, it is a very simple question. When it is not the first reaction that is labeled slow, it is a much more difficult problem. All right, so it's just simply the rate law of the first step. The first step is a slow step, and your O3 and your NO2, well, we added those two things. So they are either reactants or they are a catalyst. And those things are fine to be in your rate law. You just cannot have a reaction intermediate. So when you do the overall reaction, you see that if NO3 was part of your rate law, that would not be allowed because that is a reaction intermediate. We formed NO3, we used NO3, it doesn't show up. Okay, so again, this is the same as the last example. The rate law is simply rate is equal to K, concentration of O3, concentration NO2, because you get the rate from the rate determining step. So the slow step is the rate determining step. There is the rate law for the overall reaction. It does not include any reaction intermediates. You are done. It is first order with O3. It is first order with NO2. It is second order overall. The units for K, second order reaction, 1 over molarity times seconds. Right, so all of those things that you get from that reaction mechanism. All right, looks like the equilibrium arrows are going to look wacky here. Okay, so all these boxes are just indicating that that is an equilibrium. All right, so here we have a problem. So the first step is not labeled slow. The second step is labeled slow. This is your rate determining step. And so you would write the rate law from the rate determining step. So rate is equal to K, concentration of N2O2, concentration of H2. That would be great. That was the end of the question, the first two that were like this. But the first two that were like this had the first step being the slow step. You see now when you add up the reaction, you see that the N2O2 was formed and used up. Your N2O2 is a reaction intermediate. And so this, if you ever have a reaction intermediate in your final answer for the rate law, it is 100% chance to be wrong. You can never have a reaction intermediate in the overall rate law. N2O is also a reaction intermediate. That one doesn't matter because that's not in our proposed rate law. So when you add this up, you got two NOs, two H2s to give you an N2 and two H2Os. They already gave you the overall reaction. The overall reaction is normally not given. It is something that you just simply add up the reactions and you write the overall reaction. The steps of the mechanism have to be given. That is done experimentally. All right, so this is how we're going to get rid of our reaction intermediate. We are going to use the definition of equilibrium. All right, so it is nice since the arrows didn't show up as equilibrium arrows, they labeled it as equilibrium. What equilibrium means is the rate of the forward equals rate of reverse. So definition of equilibrium, rate forward equals rate reverse. All right, so you're at equilibrium. It is going forward, it is going backward. And at equilibrium, the rate of the forward equals the rate of the reverse. The concentrations of your NO and your N2O2 in that equilibrium are not changing. The reaction's going to the right, the reaction's going to the left. At any given time, you have the same concentrations of those. That is an equilibrium. The rate of the forward is equal to the rate of the reverse reaction. Note here that they put a K1 for the forward reaction, and then they put a K minus 1 here, and that is indicating the rate law, rate constant for the reverse reaction. All right, so to find the rate here, I'll put it up here, the rate forward. So rate sub f, forward, going to the right, it is K1 concentration of NO squared. All right, so again, these are steps in a mechanism. They are elementary reactions. We can use the coefficients as our exponents. That is a step in a mechanism. So the forward is a coefficient of 2, and so it is NO raised to the second power. All right, rate of the reverse reaction, rate reverse. That is equal to K minus 1. We're going the other way. And it is the N2O4, N2O2, N2O2 raised to the first. All right, so we're going to the left here. We're at still this reaction, except we are now going in the reverse direction. And so now the coefficient is a 1, N2O2 raised to the first, and you're going reverse reaction. So the K value is K minus 1. And so we know our definition of equilibrium. The equilibrium says that this rate for the forward is equal to the rate of reverse. And so we set those equal. And then we have our K1 concentration of NO squared is equal to K minus 1 concentration of N2O2. All right, so that is the definition of equilibrium. The rate of the forward equals rate of reverse. You write the rate law for the forward, you write the rate law for the reverse, and then you set them equal because that is what is understood by equilibrium. The rate of the forward equals the rate of the reverse. And so now we solve for the reaction intermediate. And so we simply have to divide both sides by K minus 1. So K over K minus 1 NO squared. That is equal to N2O2. You always solve for your reaction intermediate because we are now going to do a substitution. So back down here to our rate law, here is our reaction intermediate. By using our definition of equilibrium, we see that we can substitute N2O2, we have solved for it. It is equal to K1 over K minus 1 NO squared. So you do a substitution. And you get that the rate is equal to K for our N2O2. We are putting K1, K minus 1, and we're putting NO squared. And then we still have our H2. So do not forget, all we did was we have this part right here. That part has been substituted. So we did a substitution. We did our definition of equilibrium. And now you have a K times a K1 over, well, it's probably should be written as a K2. So down here, when you write it from here, it's a K2. That's a K2. So you have a K2, K1 over K minus 1. All those Ks don't mean anything. They are all constants. And a K times a K times a K is going to give you another K. So a constant times a constant divided by a constant gives you a constant. All right, so well, when we are finished, we simply have our rate is equal to K. So if you want to write K is your K2 times your K1 divided by your K minus 1. Doesn't matter. A K times a K divided by K. That is K. When you're done with your reaction, it is simply a rate constant for the overall reaction called K. All right, and then that is NO squared. And that is H2. All right, so I promised you that it would be harder. It is much harder when the second step or the third step is the slow step. You will most likely, I would say you're going to be guaranteed to be given equilibriums in order to know that your rate forward is equal to rate reverse. You're going to solve. After you get those rate forward, rate reverse, you set them equal, you solve for the reaction intermediate. Then you have to substitute that into your rate determining step, the slow step, that has a reaction intermediate in it that you have to get rid of. All right, and so now that it is finished, you see that it is second order with respect to NO, first order with respect to H2. Both of those things are reactants. That is your final answer for the rate law. And your units for K, for being a third order reaction, the units for K, 1 over molarity squared seconds. All right. So again, they're going to go through the solution. So you write step 2 is a slow step, which means it is the rate determining step. Step 2. And that's why they have K2, because you have K2 in step 2. All right. And then we're going to use step 1, which has a equilibrium. So at equilibrium, again, forward and reverse rates are equal. So you write the rate of the forward, you write the rate of the reverse, you set them equal. Then you solve for your reaction intermediate. So in order to get N2O2 on the side by itself, we simply divide by K minus 1. Then we do the substitution. Here is our N2O2, which is a reaction intermediate that cannot be in our rate law. We solve for the reaction intermediate. We stick this in there. That is equal to that. That is not a reaction intermediate, so we put that in there. And so you have your K2, K1 over K minus 1, NO squared, H2, again, K times K divided by K, a constant times constant divided by a constant. You get another constant, so you simply change that to, it is the constant for the reaction. And so it's second order with NO, first order with H2. Right, so those are the steps that you'll have to do. When the first step is not the slow step, you will have to use your definition of equilibrium, solve for the reaction intermediate, and do a substitution. All right, so catalysis, we know that that is going to make the reaction faster. What you need to know is if you have a reaction profile. All right, so here's your reaction profile. Now we add a catalyst. It is very important to know that when you add a catalyst, it starts and ends at exactly the same spot. The catalyst added only lowers our energy of activation. All right, so the dotted line means you have a catalyst. So you lower your energy of activation. So again, this is a reaction profile. Potential energy, progress of reaction. You start with reactants, you get products, and this is your transition state where you have your activated complex. And again, what is changing here is not delta H. Your products and reactants are the exact same energies. It is the change in energy of activation. So your energy of activation is lower with the catalyst. And that means the reaction is much faster. It only needs that much energy instead of that much energy. So the reaction goes much, much faster. Enzymes, you should know. It's usually a multiple choice question. So an enzyme is a catalyst. All right. So it is a selective biological catalyst. It is usually three-dimensional catalyst and very, very specific for different reactions. So enzymes are the biological catalyst. All right, so just like a reaction intermediate, it doesn't show up in the overall reaction. So a catalyst is not consumed by a reaction, so it's not a reactant. It is not something that you make. It's not a product. It is something that you add, and so it is not consumed, and so that's why we only needed 1 drop of our catalyst. You don't need very much catalyst because it is not consumed. It is still there. It's there when you start. It's there when you end. All right. All right, so here is a reaction profile, and then they added their catalyst. So a catalyst added an extra step in their reaction. This is an activated complex, then you get another activated complex. But the key is here, it lowers your energy of activation. The reaction is much faster. Your reactants and your products will be at exactly the same energy. Your activated complex is at a much, much, much lower energy. So your transition state is much lower. Energy of activation much lower. Reaction goes much faster. All right, so here's another good question. So I look at it and I say good because step 1 says slow. All right, so when the first step is slow, then this is going to be a good, easy question to get the rate law. All right, so again, here's how the mechanism is proposed here. It says step 1, step 2. That's the usual. They can write it's a mechanism. They don't have to put step 1, step 2. It's always a good thing to do. You don't have to do it. But when it says mechanism, those are elementary reactions, and you can write the rate law just using the coefficients. All right, so this time when we add up our two reactions, we see that the IO minus, we have one on each side. They are gone. We see I minus. I minus, it is gone. And so when you add that up, you got 2 H2O2, you got that yielding oxygen and 2 H2Os. All right, so of course, here are the reactants. Here are the products. All right, and so we have I minus. Note in step 1, H2O2 reacted with I minus. The only way you could have gotten there in step 1 is if you put it there. And so I minus was added to the H2O2 to get this reaction to occur. But then in step 2, when we had our reaction, it produced I minus. And so in the overall reaction, the I minus does not show up. So I minus is a catalyst. We added it in step 1. We produced it in step 2. It doesn't show up in the overall reaction. IO minus, we made that in step 1. We didn't add it. We made that in step 1, and then we used it up in step 2. So IO minus is a reaction intermediate. All right, so you need to know, it's very simple, takes a little practice, be able to label your reactants, your products, your catalysts, your reaction intermediates. All right, so now we have listed the slow step, and the slow step is step 1. So you go right to the answer. Rate is equal to K, concentration of H2O2, concentration of I minus. All right, and so your rate law, the only rule for the rate law is it cannot have a reaction intermediate. It can have a catalyst, it can have a product. Normally it has reactants, but it can have anything except it cannot have a reaction intermediate. So reactants, products, catalysts, fine. Reaction intermediate, then you will have to have some equilibrium, solve for that reaction intermediate, do a substitution to get rid of it. So here is your overall rate for this reaction. It is first order with H2O2, first order with I minus, second order overall, units of K, 1 over molarity times second. All right, so, the homogeneous catalyst means it's in the same phase. So everything's aqueous. The catalyst is aqueous. It's reacting with an aqueous H2O2. All right, so homogeneous, it's in the same phase. Now, when you do a heterogeneous catalysis, now normally you're using a solid and then something that's a gas or a liquid that goes onto that solid. So that would be a heterogeneous catalyst when you have different phases. You have normally a solid with a gas or a liquid. We're not going to do chem absorption. Okay. And there's just a picture of your reaction occurring on a solid metal surface. Hydrogenation using platinum is the most famous heterogeneous catalysis. All right, so your enzyme, again, that is a biological catalyst. All right, so you got your substrate, and it has to be a perfect fit with your enzyme substrate. Then that can break into your enzyme. Again, it's a catalyst. So the enzyme is not consumed. You start with the enzyme. The enzyme is then produced in a subsequent step. It is not consumed. It is a catalyst. All right, so you have, again, You have your reaction without the catalyst, and in biological systems, if you don't have the right enzyme, you don't have the reaction. So the reaction will take much longer, like 100 years, and it will happen when you're dead. So it doesn't happen unless you have the correct enzyme. All right, so the enzyme lowers the energy of activation, reaction goes much faster. All right, so that is the end of chapter 13. So chapter 14 is going to be extremely important. Chapter 14 is on equilibrium. So the only thing we said about equilibrium was the rate of the forward is equal to the rate of the reverse. There's going to be chapter 14, 15, 16, 17, 18, 19 dealing with equilibrium. All right, so there's lots of things we're going to cover in this chapter. All right, so we're going to do chemical equilibrium. Again, the rate of the forward is equal to the rate of reverse, which means that at any given time, nothing can have a zero concentration. If you have zero reactants, that means that it cannot go forward. If you have zero products, that means it cannot go in the reverse. So when you're at equilibrium, everything has a positive value in order for that to be at an equilibrium. All right, so the rate of the forward equals the rate of the reverse. All right, so again, the equilibrium arrows are not working on the program here. So the equilibrium arrows, you have two separate arrows, one pointing in the forward direction, one pointing in the reverse direction. All right, so at any given time, if this is at equilibrium, that means you have a concentration of CO, a concentration of H2, a concentration of CH4, a concentration of H2O vapor. All right, so you have to have a concentration of all reactants and products for that to be in an equilibrium. Okay. And again, it doesn't get to equilibrium and stop. It is constantly going forward, constantly going reverse, but at the exact same rate, which means that the concentrations, once you reach the equilibrium concentrations, they're going to stay at those concentrations. And they cannot be zeros. All right, so here is a problem. So here is our reaction. So what we're going to find whenever we're doing these problems, we're going to have initial, and we're going to have a change, and then we're going to have equilibrium. All right, and so some people will call this ICE, so because you're going to see initial, change, equilibrium. All right, so you always will go through those processes, initial, change, equilibrium. All right, so we have 1 mole of CO and 3 moles of H2 placed in a 10-liter flask. So whenever we're doing these, we are either going to be in pressures in atmospheres. These are all gases. They could be given in pressures or molarity or moles. All of those are used. I'm going to stick with molarity. So I'm going to put it in molarity almost every time. Sometimes I'll put it in pressures. If they just give the pressures and you don't need to convert it, then I would leave it in pressures. So I will use molarity or pressures. 90+% of the time it's going to be molarity. So my initial CO, 1 mole, 10 liters. So that is a 0.1000. They have 4 sig figs, 4 sig figs. All right, and so I'm simply taking 1 divided by 10. So that is 0.1 molar. Here, initially, I have 3 moles in 10 liters. So 3 divided by 10. 0.3000 molar. All right, and so that's it. It said I put a mole of CO and I put 3 moles of H2 in a 10-liter vessel at 927 degrees Celsius. They only give you the temperature because your rate constant K will change, and so will your equilibrium constant when you have a different temperature. All right, so they give you that temperature. You're going to have an equilibrium constant, but that constant is at that temperature. All right, so it's allowed to come to equilibrium. So initial, we didn't add any CH4. We didn't add any H2O. So there is no way this reaction could go into the reverse direction. It must go forward. All right, you have to go forward at equilibrium. You cannot have zero. So that tells you that the reaction is going to form CH4. It is going to the right. So when we talk about change, it tells us which way the reaction is going to go. And you have to use stoichiometry. So if it's going to the right, we know we're going to lose some amount, x. All right, and we're using coefficients. This one is going to lose 3x because that is the coefficient. And our CH4 is going to get an amount that we are going to call x. And H2O also is going to get an amount that we call x. Those x's are based on the coefficient. So we know it's going to go to the right, so we know our concentration of CO is going to go down, and it's going to go down by 1x value, minus x. We know that it's going to go to the right, we know our H2 is going to decrease, and we know it's going to decrease by a 3x amount. All right, we can't have zero, so we're going to form some, and so it's going to form an x amount because the coefficient is 1, and we're going to form an x amount here again because the coefficient is 1. All right, so now it says that we found 0.387 moles of water. And so I now have a number for x. Now I know that x is equal to your concentration of H2O gas. And that is equal to the 0.387 in our 10-liter vessel. All right, and so we get our x value always in molarity of 0.0387 molar. So now we have x. And so x, all right, so our CO is concentration is simply 0.1 minus x, which is equal to 0.1 minus 0.0387. So that is a 316, 0.0. So we have our CO concentration at equilibrium. It is 0.0613. All right, we have our H2 concentration, which was 0.1000 minus 3. X, so we have to multiply that by 3, so 0.1000 minus 0.300 minus 3x. Our initial concentration is 0.3. I'm still trying to multiply this by 3, 2, 4, 1, 1. 0.1161. And so that is a 9381 point. All right, so I'm doing all this math in my head, so hopefully that comes out correctly. And so our concentration of H2 at equilibrium, if I did my math correctly, is 0.1839 molar. And then since CH4 and H2O are both X, all right, so here, not only is that equal to our H2O gas, that's also equal to our CH4. All right, so that is the molar. All right, so again, you have to look at the words. What is the molar composition of the equilibrium mixture? Molar is moles per liter. And then it says what is, that is, how many moles of each substance are present. Okay, whatever. Molar should be a moles per liter if you're saying molar concentration. But then they say, well, actually, we want to know how many moles of each substance are present. So again, it's in 10 liters. And so you would have to multiply it by 10 to get it into moles. So times 10 liters, this is going to give you a 0.387 moles, which is what they gave you in the problem. 0.387 moles, that is moles of H2O, that is X, that is also the moles of CH4. When you multiply your CO by 10, you get a 0.613 moles. And when you multiply this by 10, you get 1.839 moles. All right, so the volume is 10 liters. All right, so if you want to change molarity into moles, and you know that molarity is moles per liter, you would have to multiply it by liters in order to get moles. Normally, we work in molarity. It is always converted into molarity because we're going to have an equilibrium constant, and the equilibrium constant can only put the units of molarity in the equilibrium constant. So molarity is how we're going to do 99% of these problems. All right, so then they go through it. You can check to see if my math is right. Yes, I think that's what I got. So good. All right, so again, you're going to have your equilibrium constant. Now, this is a capital K sub C. When you have the C here, that means that is going to be a concentration, and it's going to be concentration in molarity. So C means it's going to be concentration, and that is in moles per liter. So every number that goes into that K value is in molarity. All right, so what you do is you take the concentration of products, and then you raise that to the coefficients. And divide by concentrations of reactants. Raised to their coefficients. All right, so that is how we're going to have the expression. So that is the expression for our equilibrium constant K. Products over reactants. Very important to remember when I do KC, it is the concentration of products over reactants. Always products over reactants. All right, so if they give this and they say, here is my equilibrium by showing an equilibrium arrow, you would write that your Kc is the concentration of products, C raised to the lowercase c, and D raised to the lowercase d over, so that's your products, C, the coefficient, lowercase c, D, uppercase D, coefficient, lowercase d, products over reactants. Concentration of A raised to the lowercase a, concentration of B raised to the lowercase b. All right, so that's how you will give the equilibrium expression. Concentration of products over concentration of reactants. Now note, here they're not putting any sort of phase. All right, so your Kc only if it's aqueous or gas. Never a liquid or solid. If it is a liquid or a solid, you just ignore it. It goes in as a 1, so you don't put in a 1. You don't do anything if it is a liquid or a solid. All right, sort of like when you do your rate law, you cannot be reaction intermediates. When you do your equilibrium expression, It cannot contain a liquid or a solid. You don't have to do any math to get rid of it. You just don't put it in there. All right, so here they do put the labels. And so all of these labels are gases, and so they all go in. If one was a liquid, and that's very important with water because water can be a solid, liquid, or gas depending on the temperature or the pressure. So you have to be aware. If this says H2O liquid, we're not putting it in the equilibrium expression. This says H2O gas. All gases and aqueous will go into our equilibrium constant, Kc. So your product, CH4, raised to its coefficient of 1. You can put the 1 if you want. I'm not going to. You have H2O, raised to its coefficient. Again, it's a 1. You don't have to put it if it's 1. It is understood to be a 1. Concentration of CO, raised to the first, because that's its coefficient. And then you have hydrogen. Its coefficient is 3. So that one you have to put because it's not a 1. It is a 3. The coefficient of your H2 is a 3. If you do a units check, note that Kc, you never put units for Kc. However, in lab, I will ask you, what are the units for Kc? So there are units sometimes there's not, because it's molarity times molarity divided by molarity, and then molarity to the third. If it happened to be molarity times molarity on top and molarity times molarity on bottom, there wouldn't be any units. All right, so the concentrations are always in molarity. So here you see that molarity cancels that molarity, and this molarity changes that to a 2. And so the units are 1 over molarity squared, or molarity to the minus 2. All right. Units for Kc are not required. However, if you put the units for Kc and you put the wrong units for Kc, you will lose a point. So when in doubt, don't put a unit, unless, of course, the question says, what are the units for Kc for a given reaction? So it will change with the reaction. And it is a very important thing to know that Kc does not require units, but it does have units. Sometimes the units are, everything cancels out and it's unitless. Sometimes it doesn't all cancel out, it's 1 over molarity squared. All right, so here, again, these boxes indicate that the equilibrium arrow did not get inserted correctly. All right, so here we're going to have an ICE problem. All right, so what do I mean by ICE? That means we're going to do initial, change, and equilibrium. All right, and up here I can write the Kc. Kc is going to be my concentration of hydrogen times my concentration of iodine divided by my concentration of Hi, hydrogen iodide gas, squared. So if I were doing the units on this one, it would be molarity times molarity divided by molarity squared. So it would be a unitless Kc. They would all cancel. All right, so here, when 4 moles of Ki was placed in a 5-liter vessel, all right, so that's my initial, 4 moles per 5 liters. And if you push the buttons on your calculator, that gives you a 0.800 molar. All right. Again, they give a temperature because the rate constant would change at a different temperature. This would not be the answers you would get if you used a different temperature. At 458 degrees Celsius, the equilibrium mixture was found to contain, all right, so now it tells you where we're at. It says the equilibrium mixture. We are here. All right, so again, you got to read the question and know what it's telling you. This is telling you the equilibrium mixture. Now we're in the E, was found to contain 0.442 moles of I2. So what I know is that it contains 0.442 moles of I2. And I know that this reaction is happening in a 5-liter vessel. So I have that molarity. So initially, I put in HI. I put in 0 of the H2. I put in 0 of the I2. Only put in the HI, 4 moles in a 5-liter vessel, and the reaction occurred. I did not put any H2 or I2, which means the reaction has to go to the right. So minus 2x, again, coefficient is 2. It is going to the right, minus 2x. Coefficient here is 1, so this is plus x. Coefficient here is 1, it is plus x. So at equilibrium, you're going to have 0.8, 0, 0, minus 2x. Here, you're going to have simply x. 0 plus x is x. Here, 0 plus x is x. And then they give us information about the I2, and it says that at equilibrium, x is equal to 0.442 moles in this 5-liter vessel. And so when you take that, you get 0.0884. All right, molar. Again, I'm doing that in my head. I think that's right. All right, and so this is 0.0884. All right, and now I have to multiply that by 2. So to get my concentration of HI, I have to take 0.8 minus 2x. So 2x would be an 8671.1738. So my HI at equilibrium is a 0. That's a 2. That's 3. That's 2. And that is a 6. All right, 0.6232 molar. All right, so here is my HI. Both of these are the same H2 concentration, which is equal to the I2 concentration, which is your 0.0884 mole. All right, so now it is what's the value of Kc? So now we just plug in our numbers. I'm not going to be able to do this one in my head. Okay, so Kc is the concentration of H2, 0.0884 molar. Concentration of I2, 0.0884 molar, divided by the concentration of HI squared, 0.6232 molar squared. And then when you push the buttons on your calculator, oh boy. You get about 0.02. I'll see if I can get it right to 163. All right, so when you plug that in, 0.02. All right. 0.0201 to 366. All right, so you can go through that step by step. So you have your reaction. You started with 0.8 and 0, 0, so it has to go to the right. Coefficients, minus 2x, plus x, equilibrium, 0.8 minus 2x, 0 plus x is x, 0 plus x is x. They gave us this information in the question. They told us how many moles. We divide it by our 5 liters. So now we know what X is, and so we have the same number for this one, 0.0884. And then we have to take 0.8 minus 2x to get our 0.623. All right, and so then when you plug that into your KC setup and push your buttons, you get your 0.0201 for KC. All right, so that will be a typical question on the test. Make sure that you can do those types of problems. All right. There. All right, so we have a KC, that is concentrations. We're also going to have a KP. So KP means pressure. All right, now pressure, concentration, the units was molarity. Pressure, your units are going to be atmospheres. All right, so there's a bunch of different concentration units. For KC, always molarity. There's a bunch of different pressure units. For KP, always in atmospheres. All right, now when you're doing KC, it has to be aqueous or a gas. If it is KP, now we're talking only gases. Okay, so in KP. All right, so it will not include aqueous here. So never do they include liquids or solids, but this one also does not include aqueous. For KP, it is only for gases. So anything aqueous, liquid, or solid would not go into a KP. All right, so here they're solving PV is equal to nRT. They're solving for N over V because that is moles per liter, and so that is mRT. All right, and so when we have our KP, we use the pressure in the unit's atmosphere, which we always use for PV is equal to nRT. And for the KC, we're using molarity, which is N over V, and nRPV is equal to nRT. N is always moles, V is in liters, moles per liter. And so we see a relationship using PV is equal to nRT for our gases. And so we can then, in this equilibrium, give the expression for the KP. So how we're going to write the KP? It is the pressure of CH4, again, raised to the first. I'm going to put it here. It's the coefficient. It is the pressure of H2O. Again, you don't have to put raised to the first when it's raised to the first, but for this first one, I'm going to do it. All right, and then that is your products divided by reactants, the pressure of CO raised to the first, and then the pressure of H2 raised to the third. All right, so it's exactly the same as the expression for KC, except KC has brackets because they're molarity, and your KP is always going to be in atmospheres. So when we do a units check here, you're going to have atmospheres, you're going to have atmospheres, just like we had molarity and molarity. This is KP, we're having atmospheres and atmospheres. And on the denominator, we have atmospheres, and then we have atmospheres to the third. All right, so the units for this one is 1 over atmospheres squared, or ATM to the minus 2. All right, so exactly the same types of units that we had for KC. It was molarity times molarity divided by molarity and molarity to the third. All right, but if it is KP, so be very, very careful. If you just see a capital K and you're not looking at the other letter, that could cause some trouble because, well, you got a 50-50 chance here. It's either KP or KC. But your Kp, the units have to be in atmospheres. Your Kc, the units have to be in molarity. All right, and so the equation that you're going to get is, and it's going to be given to you on the test. You don't have to memorize it. Kp is equal to Kc RT to the delta N. All right, so it is listed there, but it's a little bit covered up. All right, so your Kp is equal to Kcr. All right, so now we're talking about the gas constant R. And so your R value, 0.08206 liter atmosphere per mole Kelvin. And 100% of the time, which means this time as well, temperature is by itself and it is in Kelvin. If your temperature, they're 99% of the time going to give you the temperature in Celsius. You have to add 273.15, put it into Kelvin, and put that temperature into your equation. Anytime you have T, capital T, temperature, it is always in Kelvin. Delta N, all right, most important one. You knew all those already. All right, delta N. Delta N is moles of gas products. You add up all the coefficients of the gas products, so the moles, N is moles, maybe it should be coefficients of the gas products, only the gases, minus the moles of reactant, so the coefficient of the reactant, gas reactants, so coefficients of gas reactants. So we're not talking about moles. We're not going to convert if they give us grams. It's the coefficients. So the coefficients of gaseous products. So here we have a coefficient of 1. Here we have a coefficient of 1. So for this one, our delta N is 2. So we add up the coefficients of our gaseous products, 1 for CH4, 1 for H2O. That is your products, minus the coefficients of your gaseous reactants. Well, CO has 1, H2 has 3. Both of those are gases, so that is minus 4. So your delta N here is negative 2. All right, and what also is important to note that that's always going to equal the units that you get here. So the equation to get it is taking your moles of coefficients of gaseous reactants minus the coefficients of your gaseous products minus reactants. Coefficients of gas products minus coefficients of gas reactants. Always products minus reactants, but only the gases. If there's aqueous, liquid, solids, you just ignore them. It is only the coefficients of the gaseous products minus the coefficients of gaseous reactants. All right. So here they give us the Kc at a temperature. All right. So you have your equation. Kp is equal to Kc RT to the delta N. All right, and so if that wasn't hiding the, there we go. Okay, so you have your Kc at 227 degrees Celsius. Again, normally it's going to give it to you in Celsius. So you plug in the Kc value that they give you. You convert your temperature in Celsius into Kelvin. All right, so you have added 273.15. So now we can put the 500 there. R value is 0.08206, and the R value must be that one so that when you are finished, when you have your units of moles per liter, you have to have an R value that has units of moles per liter so that they cancel out. You have to have an R value that has atmospheres in it because that's what Kp units are going to be in atmospheres. All right, so to get the expression what we're looking for, Kp. It is the pressure of your products. So raised to their coefficient. So pressure of CO times the pressure of H2 raised to the second power, and your pressure of CH3OH. Again, you only put those in there if they're gases. They are listed as gases. They all go in. All right. So now we have to find, so we have everything now except for delta N. So now to find delta N. All right, so products, gases, coefficients, 1 for your CO, 2 for your H2, minus coefficients of gaseous reactants, 1. Delta N is 2. All right, if you did a units check on your Kp, you would have atmospheres, you would have atmosphere squared divided by atmospheres. And you would see that you would end up with atmosphere squared. That will always match the exponent in your Kp units. Again, Kp you will never be required on a test to put the units. All right, so, and you'll never see them in the book. They never put the units for Kc or Kp. All right, but note the delta N gives you, that will always be the delta N because you only put gases in your Kp. So then all we have to do is put in the 2 here, push the buttons right on the calculator, and we have our Kp. And that is 1.60 times 10 to the second. Again, here is a Kp, full credit. They do not put the units. All right, so it is a little strange. Most numbers, if they don't have units, they are wrong. You're going to miss some points. But Kp for that reaction, they never put units for Kp or Kc. If you put them, make sure you have them put as the correct units, and in this case, it would be atmosphere squared. But any Kp or Kc, not required to put units. All right, so homogeneous, heterogeneous. Right. So now here's where I say we do not include our solids and our liquids. All right, so I'm going to add that to that, write the expression for Kc and write it for Kp. Again, Kc, need to know Kc, only aqueous and gases. Kp, only gases. All right, and then here we have a solid. We don't put anything for the solids. We don't put anything for the solid. And so our Kc is simply the concentration of CO2. And Kp, we don't put the solid. We only put the gas. There's only one gas, and that is the pressure of CO2. So your expression for your Kc and your expression for your Kp. Kc is concentration in molarity, brackets mean molarity, CO2. And Kp is pressure of CO2, and that pressure unit is in atmospheres. All right, so if you have solids, if you have liquids, you always ignore them. If you are doing Kp, you also will ignore any aqueous. For Kp, you only put in the gases. And so here we see that delta N would be 1. I see it because here is pressure. So delta N, I know, is going to be 1. And here's how you get it by the reaction. So gaseous products, so your delta N, 1 minus gaseous reactants, there aren't any. And so your delta N is equal to 1, and your units for Kp are atmospheres to the first. Right. So again, make sure when you're doing delta N, it's not coefficients of products minus coefficients of reactants. It is coefficient of gaseous products minus coefficients of gaseous reactants. All right, so now we're going to actually look at the number of Kc and see what that would mean. All right. All right. All right, so Kc, I'm going to give you two values for Kc. Kc is equal to 1 times 10 to the 8th. And then I'll have Kc is equal to 1 times 10 to the minus 8. So this is a very large number. This is a very small number. All right, so we're going to have K values that are very large. We're going to have K values that are very small. Doesn't matter if it's a Kc or a Kp. All right, but you do need to know that when you find Kc, it is your concentration of products. So it's always the products over reactants. All right, so Kc, this one that is very, very large, that means that you have a lot of products. So this favors products. All right, so you have a lot of products. A large number on your numerator divided by a small number in your denominator is going to give you a very large number. So anytime your Kc is large, that means you have a lot of products. When it's very small, that means that you have very few products. You have a very small number divided by a very large number to give you a small number. And so when it's very small, it favors reactants. All right, so if you had, here's your Kc, 1 times 10 to the 8th, and the question is, do you have more products or reactants? Well, you have a lot more products than you have reactants. It favors the forward reaction. The forward reaction is producing your products. We're going to then compare our Kc value to the reaction quotient. All right? So it's the same expression. All right, so it's the products over reactants, but it is not at equilibrium. So K is at equilibrium. Q is not at equilibrium. All right, and we will do our QC versus KC and determine which direction the reaction goes tomorrow.